Okay, so this is another talk on trace analysis and a practical application of logic programming to build a kind of embedded DSL. In this case, it's an application to a very practical and focused problem. We are teaching concurrency in a public university in Spain with a lot of students. And we have some coding assignments. And well, concurrency is hard sometimes. And there are many things that can be error prone. And our idea is that there must be some checking of the code submitted by the students. We must do as much as we can in order to reveal errors in their submissions, right? The alternative is just run some poor tests and so on. So we are going to show how we managed to obtain a practical but cheap solution by combining logic programming as a way of defining a specific language with some on-the-shelf tools that allow us to obtain execution traces from Java programs. The course is centered in Java programming, right? So we think that you can take some lessons in order to program similar systems for code analysis in other contexts. And this is available with an open license at our research group GitLab repository. And well, this is a work that elaborates on previous work, similar things by our group. On one hand, there is a particular approach to teaching concurrency based on formal specifications. We define the problem to be implemented around a state-based model. So it's a model-driven methodology. So you're based on the model in order to write the code and also in order to produce the tests and so on. This is one of the papers where this is defining and where we defend that this is useful for teaching concurrency. And also, we had some prior experience in a European project on defining coding rules for C and C++. In fact, we already defined a DSL in Prolog called CRISP for coding rules in Sugar Prolog, where we defined a lot of coding rules in use in the industry, like high integrity C++ or similar to Misra C using Prolog. That was a project that stopped in purely structural rules. I mean, rules that had to do with the abstract syntax tree of the program, rather with the behavior of the program, which operations are done in which order. And in this particular application, we are focusing more on the behavioral patterns, that you do this before than this, and you don't do this unless this condition is met. So it's more about detecting faults in the code by a post-mortem analysis of the traces of the program. So in order to understand what is happening here, what we have here is this is the basic setting on about how we grade our student submissions, right? To make an idea, we receive around 200 submissions for every 2 students, right? We have around 400 students and 200 submissions. So first we give a problem statement in natural language, and we also provide a formal specification of process interaction. So it's basically a state-based model like TLA, not exactly the same syntax, but basically we formally specify an API of atomic linearizable operations and how they interact, right? And from that, the students are assumed to produce a Java class implementation using different techniques. Okay, so what the students receive is a test report that is obtained using property-based testing from the formal specification. This is done semi-automatically. We work a lot on property-based testing of stateful systems. So this is something which we have a lot of practice. So the unit tests are generated from the specification, and they take the code produced by the students, and these are reproducible chains of codes to the API, so that if some of the tests fails, the student knows that if he or she submits again, the sequence of codes to the API is going to be the same, right? So they're going to reproduce the same errors. And what we have added a couple of years ago is, beyond the tests, this behavioral analysis of the code. So basically, we add this event tracing facility that, along with some specific knowledge that is obtained from the formal specification and the coding rules written in Prolog, produce an additional coding style report or coding rule report that is mainly used for us in order to complement the test information, so as to detect the source of the errors. I think that this is one of the best lessons learned from this system, that these two informations are complementary. And this is something that you can apply also in industrial contexts. Okay, so this is the looks of formal specification for interest process. It's very similar to TLA or VDM, if you're familiar with. And basically, for every operation in the API, this is the API. This is an idealized bank account example with operations for deposit transfers, balance, and also alerts on some low income or so. And we define the inputs, and all these operations have a special characteristic that they're all expected to behave with linear semantics. They should be linearizable, right, in the Hartley-Wing sense, right? So whatever implementation you do of this API must respect this linearizability restriction, and there are also requirements regarding liveness, deadlocks, freeness, and so on, that must be respected in the subsequent Java implementation for this. So for every operation here, you're expected to have there's going to be a Java bank class, and there are going to be 4 methods here. So basically, what you have in one of these operations like this is the pre is a standard precondition. It is something that, if it's not met about the state of the system itself, is a pronoun, is like this. It's a reference to the state of the system, which in this case is a map from account identifiers into the money you have in the account. And pre is a standard precondition, so if it fails when you call alert, then you should launch an exception. C-pre, or the concurrency precondition, is something that, if not met when calling the operation, should lock temporarily until a future state where the state meets the condition. And the postcondition in general is how the state of the system changes immediately after completing the operation. So it's a transactional semantics for the operations in the API, right? It's basically the idea. So in this case, alert doesn't change the state, but other operations like transfer, for instance, change the amount of money you have in the system. Okay, so that would be a reference operation for this. You are going to translate API methods into Java code, and you're going to implement this with some libraries. For instance, you may use a monitor library or a semaphore library or a message passing library, and these are some key operations that you have in the library. So in general, this is a method of analyzing how you are using some library in general. So that would be a reference implementation for the state. You may represent the state of the bank in this way, and that could be a reference or correct implementation for the transfer operation, right? In this case, the student could get a good grade, right? So it can get a bit tricky because you have to check in general preconditions and launch exceptions, or you have to block if the concurrency precondition does not hold, and that means using some blocking constructs in your library and so on. And you also have to unlock other threads. Maybe if you transfer money from one account to another, then you can unblock other threads that are waiting to retrieve money from another account and so on. So this code can get rather tricky in general. Okay, so what we have expressed in our coding rules DSL is a set of common errors that we have found in the submissions. So like you should only call enter once, because if you enter and leave the monitor several times in one of those operations, you lose atomicity, right? So you can have interference with other operations. That's quite obvious. Or for instance, you should only launch one signal per API operation, because the semantics of repeated signals can get very tricky, and reasoning about problems with many signals is complex, so we forbid that, and so on. And the same with the blocking operations like the awaits in monitors and so on. So in general, our experience on about what kind of errors do the students make has been condensed into a set of common error that we are going to represent in our DSL, right? Okay, so let's go with this first part, which is the collection of the traces from the execution of the submissions. We use for this a library called Byteman for Java, or Java Byteman, that allows us to specify rules on different events that happen in the execution of a Java program. This is one example of one Byteman rule that is used to launch events when the code of the students is calling some monitor operation, right? It's calling the enter operation in a monitor, right? So this is something that can be tailored to call some particular method by us that can output some Prolog fact. So in the end, when you apply this on a piece of Java code, then you're registering some events, and if the code finally calls a monitor enter, some Prolog fact with this information, where this is, for example, this is the identifier of the thread that launches this, what is called, and so on, and a lot of information. So the first thing we do is to gather information on the execution of the code using this Byteman library, and create a very big event database stored in Prolog, right? Sorry. No. Okay, so in the end, this is a lot of pieces of trace information that we capture, and you have the detail of this in the paper. Okay, so after we collect this information in the trace, which is a Prolog fact database for some key events that happen in the execution of the submission, then we pass on to the trace analysis. So trace analysis have these three parts here, combines these three information. This is some specific knowledge about the properties of the expected properties of the actions in the formal specification. These are the coding rules that translate the good behavior that we expect from the code regarding execution properties, and this is the event trace log that get here. So The resource-specific knowledge is, well, it's not very interesting. It's about properties of about the arity of the operations, some specific details. For instance, there are some operations that do not block. For instance, deposit and balance do not block, so we mark this, and so on. Or whether they may throw an exception before actually executing or something like that. In the case of alert and balance, they don't change the state of the shared resource. So this is something that we need to know from the specification. And then we have the translation into Prolog of all the coding rules that we have. So the coding rules are Prolog predicates that reason about the event fact database that is gathered by Byteman as the different events of calls that happen in the program execution. So I have shown here a couple of them. So this is the negation of the rule that states that you should call enter only once in one of the operations of the API. So this is a Prolog rule that reads the different facts that are stored in the trace database, right? So in this case, we are using just existing facts, and in this case, we are just checking that the set of calls is of length 1, not of length 0, and not of length greater than 0. So in this case, this is quite simple, but we also have more complicated rules that, for instance, you should not signal until you haven't completed a transaction. You should signal other process when you have completed one transaction, you have changed, you have submitted all the changes in the transaction, and only in that case you should signal another thread, right? So in this case, we are using aggregation, we're using find all, we are traversing the event database, and then we are checking this, right? So we have a lot of coding rules. They are not trivial in general, but they do not get much larger than this. So if we, for instance, we detect that the students are doing some strange trick or something, it is very easy for us to define a new rule in Prolog and look for that behavioral pattern, that you're calling this before this or something like that. So for showing one example of the kind of errors that sometimes we discover and we don't expect them, some errors have to do with, for instance, dealing with preconditions in the wrong way. So for instance, we have two operations in the bank example that could launch an exception. One of them is alert. So if you're programming an alert on an account that doesn't exist, then you should launch an exception. So the precondition for alert is that the account identifier must be in the map from accounts to the money. So in general, if you're programming this with a monitor, you must first access the monitor in order to guarantee exclusive access to the table, then check the precondition, and if the precondition is not met, you should launch an exception, but only after releasing the monitor, because if you launch the exception without releasing the monitor, then you are forbidding the access from other threads. So typically, there are two kinds of errors associated with this. One is that you access the state of the bank without getting exclusive access. And in that case, this might get unnoticed by the unit tests, because the only possibility that you detect this is that there is a race condition, but some of the time you don't get a race condition. So that would be a wrong access that is not detected by the test suite, but the rule checker detects that. So if our coding rule checker detects that you're trying to access the state, but you didn't perform an enter on the monitor first in order to ask permission for exclusive access. So in that case, that would be the error that is produced. So we know that some submission is wrong, even if a unit test does not fail. And the other possibility is that they gain exclusive access to the monitor, they launch the exception, but they do not release the exclusive access. In that case, the unit tests are going to catch this error. But the problem is that the error is going to appear caused by the next thread that tries to access the monitor, because the monitor is taken, and it's going to provoke some kind of deadlock in the rest of the system. So we obtain a failure in the unit test, but the failure doesn't point the actual cause of the problem. So in this case, we obtain a message by the coding rule checker that, along with the unit test, tells us what is really going on that is causing the runtime error, right? So these are actual numbers from 209 submissions, where we program all these coding rules, and we find errors in, in average, in 35% of the submissions. 1/3 of the submissions had some kind of error, right? They were very strange errors or very common errors. Right? So when you're grading such a number of submissions, this is really helpful. Right? For the students, the tests are useful because they tell them that something is going on. But for us, if we see that something is very common, it allows us to send some message or something, telling them, okay, you're doing something very, very wrong. Right? So this is very practical. But I think it can be also practical if, for instance, you have a huge base, a huge programmer base in a company, and you're doing a lot of submissions or commits. Okay, so basically the conclusions, the good conclusions is that this kind of behavioral rule checking is an effective way of complementing the information that unit tests provides, right? Because sometimes you don't know what is the actual cause of the error. This is very cheap. I mean, we didn't have to do a lot of things. I mean, Byteman produces just events that can be written onto a file. We use Prolog as a fact database, and then we define very declaratively the rules by traversing the event database using Prolog rules. This has been very, very simple, relatively simple. And we have incorporated this as an essential tool for grading the submissions. Limitations of this, one of the limitations of this is that this is behavioral. This doesn't work on the source code. So that means that it only detects wrong traces if those wrong traces are actually executed by the unit tests. So you need that the unit tests have a very good coverage in order to discover the problems in the source code, right? Fortunately, we work with unit tests that have been obtained automatically using property-based testing from the formal specification. So they have a very good coverage. We have improved this over the years. So in the end, if there's something wrong in the code, we usually discover this using this combined attack between the coding rules and the unit test, right? And as future work, there's always further possibilities of integrating this, especially with other tools that actually look at the source code and other static analyzers. Thank you. That's it.
Thanks for the presentation. At our school, every professor has different ways of coming up with some system to test 100, 200, 600 students' programming assignments. I'm of a philosophy that the test that I use to grade their code, the student should have access to my tests. Other professors have the idea, no, the student should not see the tests because then they can reverse engineer them. What's your opinion?
On both, in some sense. Okay. So it's true that students perform reverse engineering if they know the tests, right? But in this case, what we do, they don't know the tests, but they receive the sequences of calls. So if the test fails, we tell them, okay, there are, for instance, 10, let's say 10 unit tests that are 10 sequences of, let's say, 10 calls, right? So in the whole, you have like 100 calls to the API, right? So if the test is okay, you don't say anything. If the test 1 passed, test 2 passed, test 3 failed. And test 3 failed in the 7th call. So the first call is, we call deposit, fetch, alert, blah, blah. And here, the behavior is not what we expected, because this alert should have awakened this thread, for instance. So we only give the essential information for them to know that something failed, but we don't reveal all the unit tests, and we change it. So we have several submissions, and we have a first stage and then a final stage. In the final stage, we learn from their mistakes, and we strengthen the tests.
How do the students test their own code?
No, in the case of concurrency, it's very hard for them to obtain a good coverage in the unit test. So we have our own submission system. We have a server running these tests all the time with virtualization and so on, because otherwise the bad submissions take all the CPU from the good submissions. And it has taken a lot of work from us, and that's it. The fact that the tests are deterministic is essential, because if they make a submission and they have only 2 errors, they need to know that in the next day they're going to attack the same tests, right? So we don't change them very often, right? They are given a kind of mock-up system, right? So several threads that call the API, so they can change it while they're developing, and they do random calls and so on. So if they want to make their own tests, they can do that. So they only submit when they have randomly tested for several threads and so on, that more or less the behavior is sensible. But when they submit to our unit tester, the coverage, we cover corner cases because we have generated that with the PBT technique. And that's much harder. It usually reveals errors that they did not think about.
Thanks. So would it be possible to adapt this kind of tool to checking things that aren't necessarily runtime errors? And the reason I ask is because, at least in the past year or so, there's been a lot of interest in trying to detect whether code has been written by ChatGPT, for instance, as opposed to a student. Is that more of a static analysis sort of task?
I haven't thought of that. I mean, the origin of this is, of these coding rules and behaviors, lies in embedded systems, from avionics, motors, and so on. So this comes from 20 or 30 years ago, and we didn't have this problem of code generated and reused. And we are now a project for dealing with that kind of code, but I haven't thought about whether this kind of behavioral analysis can reveal. Sometimes it depends on the application domain. Sometimes ChatGPT produces good code because it copies from the good sources, and other times the code obtained from ChatGPT is quite strange. And so I don't have a general answer for that.
Regarding one of the limitations that you mentioned, which is the generation of test cases. You mentioned that you use property-based testing for that, but that's based on random test case generation, I think. So have you considered to use a concurrent tester, which typically gives a better coverage, or even a model checker if the number of states is finite, and so that you can check every possible execution up to partial order reduction?
Yes, it's always in our agenda. We didn't do that, but we want to do that because, as you know, I mean, one of the limitations of black box testing can be overcome with this kind of things. So yes, we plan to do that in the future.
There are many mature tools for
yes.
testing, for instance.
Yes, no, it's just a matter of of time. And this works because, I mean, if you want to capture errors, you do with that. I mean, probably for a more exhaustive industrial application, a better combination of techniques is needed.